Hello, everybody. This is Mr. Fasoni, and this is the video for 8.3 from the chapter 8, Sequences and Series. So in class, we talked about 8.3. We went over the lecture, and it was about analyzing geometric sequences and series. So just like the arithmetic ones, the geometric sequences and series have a repeated operation that's happening. And in this situation, the repeated operation that's happening is multiplication. So we're multiplying every time we go from one position to the next in this sequence. Remember the arithmetic ones we were adding. So in this chapter, we identified, wrote the rules for, and found the sums of finite geometric sequences and series. And again, a series is just the sum of a sequence, and a sequence is an ordered list of values that have a specific rule that generates them. All right, so we talked about the geometric sequences, and again, the only kind of difference here is instead of a difference, we have a ratio, and I should have used pink for this. So remember, with the arithmetic sequences and series, we had a difference. Now we've got a ratio. This is just the thing that we're multiplying by with each step. So the first thing that we did was identify whether each sequence was geometric or not. So a geometric sequence is found if we have the same ratio from each step to the next, or each position to the next. So to find that, sometimes it's easy and obvious, sometimes not so easy and obvious. So one way we can find that is we can just take any two values that are next to each other, like 3.2 and 0.2, and you divide the second value of the two by the first, or the later value in the sequence by the previous value. So if I do 3.2 divided by 0.2, that's going to give me 16. So that's my ratio. I'm multiplying by 16. Well, then to test that, all I need to do is see if the ratio is going to be the same the whole way through. Well, I can either divide again. I can take negative 12.8 and divide by 3.2. If I do that, I'm going to get, well, I can already tell you it's going to give us a problem, because negative 12.8 divided by 3.2, 12.8 divided by 3.2 is 4, but since it's a negative, it's going to be a negative 4. So not only am I, not only is my ratio not the same, they're not even, one of them is positive and one of them is negative. So I multiplied by 16 the first time, negative 4 the second time. At this point, I've got two different ratios. Remember, as soon as two of them are different, we know that this is not going to be a geometric sequence. So I can go to the next one, and I can just do the same thing I did before. Take negative 1.5 and divide it by 0.3. And in this case, I'm going to get negative 5. So my ratio is negative 5 for the first step. And then if I test it again, 7.5 divided by negative 1.5, I actually get negative 5 again. So I'm multiplying by negative 5 yet again. That looks like a decimal. Let me change this around. It's kind of hard to do this. A dot, negative 5, multiply by negative 5. And sure enough, if I keep on doing this, every time I'm multiplying by negative 5. Another way we can test this, you can do the first one. You can use a calculator. 1.5 negative divided by 0.3, we get negative 5. So if I then take 0.3 and multiply it by negative 5, I get negative 1.5. If I hit the enter key again, or the equal sign again, I get 7.5, negative 37.5, 187.5, and so on and so forth. So that's an easy way to test all those values very quickly. So in this case, it is a geometric sequence. On this next one, I've got fractions. Don't let fractions freak you out. They're just numbers like all the rest. So all we need to do is take 1/6 and divide by 1/2. Well, if I'm dividing fractions, remember, or if I've got a fraction with fractions in the numerator and denominator, I can turn it into just a straight division problem that looks like this. And then remember, division is the same as multiplying by the reciprocal, so I can then change this to multiplying by the reciprocal. 1/6 multiplied by 2/1 is going to be 2/6, which is 1/3. So my ratio in this case is 1/3. So then I can test this again. If I look, if I multiply by 1/3 again, this 6 is going to be multiplied by 3, and that's going to give me 18. So it looks like it holds. And if I test it again and again, 18 times 3 will give me 54. 54 times 3 will give me 162. So again, this is a geometric sequence. And then the last one, I've got 1/4, 1/16, 1/64, 1/256, and 1/1024. And if I do this again, 1/16 divided by 1/4, I'm going to get something that looks like this. So my ratio is 1/4 on the first step. And then I can just test that again. And sure enough, if I multiply by 4, 16 by 4 multiplied by 4 is going to give me 64. If I multiply 64 by 4, I get 256. And 256 times 4 is going to give me 1024. So again, all these jumps have the same ratio, and it is a geometric sequence. All right, next up, we went over the rule, the general rule for these geometric sequences. We had 2 values that matter, A1, which is the most important value, and then in this case, we've got a ratio. In the previous ones with arithmetic, we had a difference, and we have this equation that kind of sums it all up, or puts it all together. I shouldn't say sums it all up, because that has to do with series. So position AN, or the value at position N, AN is the value at position N, is going to be A1, which is the first value, times R, my ratio, to the N minus 1 power. Just remember that this N minus 1 power right here represents the number of steps, or the number of moves, or the number of multiplications, or the number of jumps, or whatever you want to say, from the first position to the nth position. And then we had 3 different types of problems that arise from this, growing in difficulty at each step. The first one was where we just needed to write the rule for the sequence and then come up with A10. So if we need to do this, remember our kind of format for this, AN is equal to A1 times R to the N minus 1 power. Well, I just need to find the 2 values. Remember, my A1 value is always the first value. So in this first equation, my A1 value would be 4. And then my ratio value, I can just find by either just kind of inspecting it, or if I can't see it immediately, I can always take the second value and divide it by the first, or the fourth value and divide it by the third, or whatever order I want to go in, as long as they're next to each other. 20 divided by 4 is going to give me 5. So I'm multiplying by 5 at each step. That means my ratio is 5. So I plug that in, and then the rest of my equation is kind of generalized because I'm looking for the value at position N. If I plug in an actual value, then I can find the value at that position. That's kind of a weird way to say it. If I plug in an actual position number, I can find the value at that position number. And it asks us to find A10. We want to find A10, that's just going to be equal to 4 times 5 to the 10 minus 1 power. Well, this is going to be kind of a nasty number because it's going to be 5 to the 9th power. I don't know what that is off the top of my head. So I'm going to use my calculator. 5 to the 9th, 1,953,125. So it's going to be 4 times 1,953,125. Did I get that right? Let's check. Yes, I did. So I'm multiplying those together. I could do that manually, but why do that when I've got a calculator? 7,812,500. 7,812,500. That's my 10th position in the sequence. So if I were to continue this out, every time I'd be multiplying by 5, I would eventually get to the point where my number is 7,812,500. All right, let's do the next one. These are from the book, by the way. This is 15 and 17 from the book. So again, I need to find my A1 value. Well, there it is, 112. And I need to find my ratio. And maybe you can see it, maybe you can't. If I look at these two, I can definitely tell I'm just dividing in 2. So I'm really just multiplying by 1/2 at every step in this sequence. Remember, these are given to us as geometric sequences, so we don't need to test them all. We just need to find the ratio anywhere in this because the ratio is going to be the same. So I know that my ratio is 1/2, and I know that my A1 value is 112. And then from there, I can quickly build my equation. And then from there, if I want to find a 10, for instance, it's just going to be 112 times 1/2 to the 10 minus 1 power. That's going to equal 112 times 1/2 to the 9th power, which is going to be 112 times 1/512. If you're wondering how I got that, it's just 1/2 to the 9th, which is the same as 1 to the 9th over 2 to the 9th. 1 to the 9th is just 1, and then 2 to the 9th is 512. This is kind of messy. I can try to do it by hand. 112 times 1/512. Well, I know that 512 is divisible by 2 because it's a power of 2 and it's even. So I'm going to divide both 112 by 2. That's going to give me 56. And 512 by 2. That's going to give me 256. I can probably divide by 2 again. 128 and 28, and maybe divide by 2 one more time. What's that? 64, and 28 divided by 2 is 14. I got 14 over 64. I'm just rewriting these because I'm running out of room. I can write that. I can divide by 2 one more time. That's going to be 7 over 32. So this value is at its 10th position is going to be 7/32 seconds. Or in other words, the value at position 10 is 7/32 seconds. All right, let's go to the next ones. So these ones are a little bit tougher. In these situations, we're given the value for R, and we are given the value for one term. But in this case, the term that we're given is just a random term in the sequence. So to fix that, what we can do is plug in what we know and then solve to find A1. So in this situation, remember let me write this actually over here. Our equations are AN equals A1 times R to the n minus 1 power. Well, all I need is, I need to find A1. That's the thing I don't know, but I do know my R values. So what I can do is I can plug in the value that's given to me, this extra value, and that's going to help me replace this AN and the N value. So if I go ahead and do that, A4 is negative 192. That's going to be equal to A1, I don't know that, times my ratio, which I definitely know, that's 4. And then my exponent is just going to be my N value, or 4, in this case, minus 1. From there, I can do some order of operations on the right side of the equation. I'm going to have negative 192 equals A1 times 4 to the 3rd power. I'll just continue doing this. Negative 192 equals A1 times 64. And then after I've done all the order of operations stuff I can on the right side of the equation, I can divide both sides of the equation by 64. By doing that, 64 goes away on the right, and I end up with negative 192 divided by 64 is actually negative 3. So my A1 value is negative 3. From there, I can build the rule. So the rule on this one is going to just be AN, the value at any position I want, we call it N, is going to be the value at the first position times my ratio, which is 4, to the n minus 1 power. There's my rule. So they come together really quick once you get the hang of it. Let's do this bottom one really quick. So again, I don't know A1, but I definitely have A5. A5 is equal to 3, so it's going to be 3 equals A1, no clue yet, times my ratio. My ratio is negative 1/3. This is going to be a little bit funny. To the n, it's going to be 5 minus 1 power. So again, I just do order of operations stuff until I can't do anymore on the right side of the equation. So I have negative 1/3 to the 4th power on the right side. If I multiply that out, or if I exponentiate that out, well, actually, this won't be helpful. It won't give me the fraction. So I'll just show you guys in the video. It's going to be negative 1/3, well, negative 1 to the 4th over 3 to the 4th. That's very small writing. Let's redo this a little bit. Negative 1 to the 4th over 3 to the 4th. Well, negative 1 to the 4th power is going to be positive 1. 3 to the 4th is not 27. That's 3 to the 3rd. 3 to the 4th is 81. So that I can rewrite this. Uh-oh, running out of room. Let me zoom in a little bit. So I can rewrite this as 3 equals A1 times 1/81st. Well, if I divide both sides of the equation by 1/81st, then I end up with 3 divided by 1/81 equals A1. I can work this one through. That's going to be, let's continue going to the right. So that means it's going to be the same as 3 divided by 1/81, which is the same as 3 times 81, which is going to give me an A1 value of 243. So if I wanted to write the rule out, I've got the A1 value, I've got the ratio, so it breaks down to the following. AN is equal to my A1 value, which is 243, times negative 1/3 to the n minus 1 power. That's my rule, and I can use it to find A100 if I wanted. All right, last one, writing a rule given 2 terms. So in this one, we don't have the R value or the ratio, the ratio or the A1, the value at the first position. Well, in some we don't. Looks like in this first example we do, actually. That's kind of strange. But what we end up doing is we can create 2 separate equations and use those to figure out some stuff. Number 35 is kind of a rare exception. In this one, we actually do have the first value. Kind of strange. So my blue equation is going to be my first value, and my yellow equation is going to be my second value. So what I'm going to do is I'm going to set up 2 equations. This is very strange. So if I use the general form of the equation, let me write it again really quick. AN equals A1 times R to the n minus 1. So if I multiply this out, or if I, fill this out, A1 is just, well, negative 6 is equal to, well, there's A1 again, times my ratio. I don't know my ratio. And then my n minus 1 in this situation, actually, I'm going to leave this all blue. My n minus 1, my n in this case is 1, so it's going to be 1 minus 1. If I work this through, it's going to be -6 equals -6 times r to the 0 power. R to the 0 power, well, anything to the 0 power is 1, with the exception of 0, but we're not going to worry about that right now. And if I continue to work this through, I don't really get anything interesting. I just get -6 equals -6. So not very helpful, right? But what I can do is I can go on to the next equation because I actually have my A1 value. It was given to us. It's kind of a strange situation. So I can go to my next equation and I can plug in what I know there. -486 is equal to my A1 value, which is -6, times my R value to the n minus 1. Well, I know my n in this situation. My n is going to be 5. So to the 5 minus 1 power. So I really have -486 is equal to -6 times r to the 4th power. Well, I can use this to solve for r. I divide by -6 on both sides of the equation. These cancel out. Actually, let me change my color. I'm solving for r, so I'm going to use pink. Divide by -6 on both sides of the equation. Cancel, cancel. These negatives become positive. 486 divided by 6 gives me 81. So 81 equals r to the 4th. Well, 81 is just 3 to the 4th power, so that means that 3 equals r to the 4th. Oh, not r to the 4th, r to the 1st. So now I know my r value, and they actually gave us our A1 value at the start. It's kind of a weird problem, but now I can just fill in what I know to build my equation for any value I want to find. AN equals A1 times R to the n minus 1 power. All right. So that's 35. Let's do 37. That one will hopefully be a little bit more interesting because we actually have two values that are both unknowns. We have, let me section this off again. So we have A2 is equal to 64, and we know that A4 is equal to 1. So if I build two equations using the same format, A2, which is 64, is equal to A1 times R to the 2 minus 1 power. That's my first equation. My second equation is going to be A4, which is 1, which is equal to A1 times R to the 4 minus 1 power. So let's do some order of operations stuff on both of these. There's not much we can do, but I can at least simplify my exponent, R to the 1st power. And on the second one, it's going to be 1 equals A1 times R to the 3rd power. Now what I'm going to do is I'm going to solve the left side equation, doesn't matter which one, I'm going to solve it for R. Oh, I'm sorry, I'm going to solve it for A1. Apologies. To solve it for A1, I'm going to divide both sides of the equation by R. So 64 divided by R is equal to A1. This doesn't give us the value for A1, but it tells us the worth of A1 in terms of R. If I knew what R was, I could figure out A1. Or if I knew what A1 was, I could figure out R. But I don't know either. But what I can do now is I can use this 64 over R in the place of this A1 right here. So my right equation now becomes 1 equals 64 divided by r times r to the third. What happens here is if I've got a division by r and a multiply by r to the third, I can cancel out this r and I can cancel out one of the r thirds, or one of the r's that make up r to the third. And now I'm left with 1 equals 64 times r squared. I'm almost done. Now I'm just going to divide both sides. If I want to find the value for r, I can divide both sides by 64. I end up with 1/64 equals r squared. Well, if I look at 64, square root of 64 is 8, so really 1/8 is going to equal r. So 1/8 is my r value. Now that I have that, I can plug that r value back into either of the equations. I'm going to do the left side equation. So I'm going to take 64 equals a1 times r. That was this equation right here before I started canceling stuff and moving stuff. Well, if I know r, let's change that out for 1/8. If I want to solve for a1, all I have to do is divide both sides by 1/8. These 1/8 cancel, and now I'm left with 64 divided by 1/8 equals a1, which is the same as saying 64 divided by 1/8 like this, which is the same as saying 64 times 8 over 1. 64 times 8 over 1, or 64 times 8, is 512. So 512 is equal to a1. I've got my r value already, so now I can build my equation. An, the value at any position I want, is equal to the value at my first position, 512, times my ratio, 1/8, to the power of n minus 1, which just represents the number of multiplications I need to do, or steps I need to take, or jumps I need to make to go from position 1 to position n. All right, so that's the three kind of different ways we can do these problems from easiest to hardest. And by hardest, it's really just most time consuming because we just have to find those variables and we have to kind of work these equations a little bit. So then the last thing we had was the sum of a finite geometric series. And again, the things that matter in this situation are finding the ratio value and finding the a1 value. So this is saying that the sum of the first n terms of a geometric series is equal to the value at the first position times 1 minus the ratio to the number of positions or number of terms over 1 minus the ratio. So this comes together very quickly because there's not a lot of stuff that we have to do. We already have a lot of information. If you look at this summation notation, I'm starting at 1, I'm going to 10, and my rule is 7 times 4 to the I minus 1 power. This tells us everything we need to know. This number up here, since I'm starting at 1, I'm going 1 through 10, so there's 10 terms or positions in the sequence that we're going to add together. So I know that the sum I'm going to be trying to get is S10. And that's going to be equal to, well, what do we need to know? We need to know the A1 value, the value at the first position. Well, I can find the value at the first position by just plugging 1 into this equation. So my equation is 7 times 4 to the 1 minus 1. Well, 1 minus 1 is just 0. 4 to the 0 is just 1. So my value of the first position is going to be 7. And then the last thing I need is that 1 minus r to the n over 1 minus r. I need to figure out my ratio. Well, the ratio is the thing that I'm constantly multiplying by as I move through the series or move through the sequence. If you look at this rule, the thing that's being multiplied multiple times is that 4. remember, an exponent is just a way of saying repeated multiplication. So if I'm multiplying by 4 repeatedly, that must mean that my ratio is 4. And then the last thing I need is that n value. Well, my n value is 10. This is going to be a mess, but I can calculate it. So let's go ahead and do it. I'm still going to have 7 on the outside. Let's deal with those exponents. These are going to be kind of messy. 4 to the 10th power, that's going to be a million something. I think, well, it's the same as 2 to the 20th, so it should be, yeah, 1,048,576. And then 4 on the bottom. Okay, kind of a mess, but easy to simplify. 7 still on the outside. 1 minus 1,048,576 is just going to be negative 1,048,575. 1 minus 4 is negative 3. Okay, again, get out the calculator or do it manually. So I've got negative 1,048,575. I divide it by negative 3, and I get 329,525. So I have 7 times 329,525. And then I'm just going to, oh, not 29, 49,000. That'd be a difference. 349,525. I'm going to multiply that by 7, 2,446,675. And there's my answer. $675. So the sum of the first 10 terms of the sequence is 2,446,675. All right, let's do one more. We'll pick up the speed a little bit. We're going 1 through 8, so my n value is going to be 8. My ratio is going to be the thing I'm multiplying multiple times. It's going to be 1/3. All I need to do is figure out my A1 value and I'm set. Well, we know A1 is just going to be 5 times 1/3 to the 1 minus 1 power. That's 5 times 1/3 to the 0, which is 5 times 1, which is just 5. So A1 is equal to 5. Should outline that in orange. That's what I've been using for A1. So I know A1. Now I just need to build my sum. The sum of the first 8 terms is going to be equal to A1, which is 5, times this fraction, 1 minus my ratio, which is 1/3, to the 8th power, all over 1 minus 1/3, which is also my ratio. And again, this comes together very, very quickly. So that's just going to be 5 times 1 minus, I don't know, 1/3 to the 8th power. That's going to be 1 over, I'm going to try to leave this in fraction form. 1/3 to the 8th power is the same as 1 to the 8th over 3 to the 8th. I don't know 3 to the 8th off the top of my head, but I can calculate it. Actually, I think I do know it, but 6,561. I'm leaving it in fraction form for a reason, which you'll see in a second. So 1 minus 1,600, or 1 minus 1 over 6,561. I can rewrite that. So my outside of the parentheses stays the same. 1 minus this little tiny fraction is just going to result in almost a whole up top. And then in the denominator, it's going to be 1 minus 1/3, which is 2/3. Okay, this is kind of messy, but let's continue it. 5 times, I'm going to change this fraction with 2 fractions in the numerator and denominator into a division problem. And then division problems are just multiplying by the reciprocal. All right, well, I can either multiply right across, or I can try to simplify. I'm going to try to simplify. So just know, we know that this is a multiple of 3 because that's 3 to the 8th power. So I'm going to divide this 3 out and this 3 out. This 3 becomes a 1. If I divide 6,561 by 3, I get 2,187. And then I can also divide both of these other two. The numerator is divisible by 2, and this is also divisible by 2 because it's 2. 6560 divided by 2 is going to be 3,280. Well, now I've got something that's a little bit less messy. It's going to be equal to 5 times 3,280 over 2187. Still kind of crazy though. Well, I can multiply this out. 5 times 3280 is going to be 16,400 over 2187. And that is really as far as I think we can take this. I don't think we can divide this out. This is a multiple of 3, and 16,400 is not divisible by 3. Yeah, it's a decimal. So this is going to be our value. It's kind of ugly, but that's our sum. The sum of the first 8 terms is equal to 16,400 over 2,187. And we're done. All right, everybody, I hope this is helpful. I will see you all in class. Have a great day.